Hello, thank you for your kind introduction, and first let me thank the organizers for the invitation. It's a pleasure to be here. As you heard, I am here to talk about approximate tensor network contractions for discrete optimization, and this is kind of interplay between employing tensor network methods in the context of spin glasses, but with the motivation coming from quantum annealing. We are witnessing a significant progress in the development of quantum simulators. For instance, a paper by Andrew King discusses the simulations of non-equilibrium quantum many-body dynamics. And in this context, it is widely believed that tensor networks are the best classical reference methods. For instance, PEP's tensor network was used there to simulate those coherent quantum many-body dynamics. And a few years ago, an algorithm based on the tensor network was proposed to solve optimization problems on a chimera graph. As opposed to those dynamic techniques, in this paper, tensor networks were used to represent classical thermal states and extract information from those thermal states. And this approach was very successful for the optimization problems defined on the chimera graph. We were interested in finding out whether we can use a similar technique to the new annealing geometries, such as Pegasus and Zephyr geometries. So first of all, can it be done? Because Pegasus and Zephyr, they are like chimera, they are sparse, they are two-dimensional, but they have much higher level of connectivity. Tensor network, they work well for low-dimensional problems, I would say up to two-dimensional problems. So first of all, we had to ask ourselves how to formulate these problems so that they are viable to standard to tensor network methods, and then how to contract them to extract information from them. And evaluating how those contractions would work in those cases, it required testing. And at the very beginning, I can say that the application of tensor network methods to the Pegasus and Zephyr geometries, it was extremely challenging. So in this talk, I will briefly tell you how we set up our algorithm, and then I will show you the results of a tensor network method, but compared with the wave quantum annealer and simulated bifurcation machine used as a second classical Ising solver. And if time allows, I would like also to briefly mention our ongoing efforts to generalize the tensor network method-based technique to more general geometries, like with all-to-all interactions. Okay, so what are the main steps of our algorithm? It is based on the branch and bound algorithm in the probability space. So it allows us to search for low energy states, as we claim that the low energy states are the most probable ones. And tensor networks are incorporated into this algorithm at the probability calculation level, as they represent classical Boltzmann distribution. And we also try the option for local dimensional reduction of those cluster degrees of freedom using loopy-Belief propagation. And I'm going to elaborate on these concepts later during this talk. So we are interested in quasi-two-dimensional graphs which are relevant to current quantum annealing processors like Pegasus geometry and Zephyr geometry. Here on the left-hand side, you may see the Pegasus graph. Spins are the black dots, and couplings between them are gray lines. And to apply the tensor network method, which, as I said, works well for low-dimensional problems, we had to use a quasi-two-dimensional structure of this graph. So the simplest way we can do this is to group spins, which, let's say, naturally builds unit cells into unit cells. In the case of Pegasus, you may see this, it's 24 spins per each unit cell. In the Zephyr graph, it's 16 spins per unit cell. And after this grouping, you obtain a simplified structure. We call it Potts-Hamiltonian, and in the following slides, we will be working with those clustered structures, not with the Pegasus graph, but with those Potts-Hamiltonians. And similar approach works for Zephyr, except from that in Zephyr we have 16 spins in every unit cell. Okay, so our goal is to identify low energy states from exponentially many possible spin configurations. And we do this by finding the most probable states according to Boltzmann distribution at some inverse temperature beta. And we claim that finding the low energy states is equivalent to finding the most probable states. We use branch and bound strategy, search strategy. So we sweep through our two-dimensional system cluster by cluster, and at each step we identify the set of states with highest probabilities using those approximate contractions of Pep's tensor network. And then we branch those states. So let's say we are here in the nth cluster, means that we know the configurations in the first n clusters, and we move to another cluster. So to branch these states, we had to add every possible values in the next cluster. Then we calculate their probabilities, and then we start bounding those states. We are doing this in 2 steps. So first, we use the locality of interactions to group states according to their boundary configurations. And we select only the most probable configurations. And discarded configurations, they encode excitations in the system, and they enable us to map a low energy spectrum. So this is the single step of a sweep. So then we move to another cluster, we repeat the procedure. We continue those branching and bounding until the final cluster is processed. In the end, identifying the ground state candidate and low energy excitations. To employ the branch and bound algorithm, it is crucial to effectively compute the probabilities. In our approach, we represent all probabilities using the two-dimensional projected entangled pair states tensor network, also called Pep's tensor network. For a classical system, and we are interested in a classical system, the construction of a thermal state is exact and is equivalent to the representation of its partition function. So in our representation, we had to define different various kinds of tensors. For instance, we have those red tensors called side tensors. They encode local energies in the system. We also introduce those squares, which are telling us about the two-side interactions. And also we introduce the purple circles, the mediating tensors, which are carrying information about the diagonal interactions. And after performing such a tensor network representation, we obtain two-dimensional structure called Pep's tensor network, and this is a structure that is viable to a standard tensor network contraction method. And we can approximately contract it to extract to calculate those probabilities. Why approximately contracted? Because finding the ground state of a general Ising spin glass problem is NP hard. And in the context of tensor network, this hardness manifests itself in the fact that the general Pep's tensor network, to contract the general Pep's tensor network, it is sharply hard. So it's even harder than NP because it contains information not only about the ground state, but also about the full low energy spectrum. That's why we use approximate contraction techniques. Thankfully for us, there are those approximate contraction techniques. However, using them makes our method heuristic, and in the end, we do not have the certification that what we have found indeed is a ground state. And we adopt boundary matrix product state contraction method. So we approximate tensors in the gray box on the left-hand side by the tensors in the gray box on the right-hand side. This is a very simple method because we are contracting row after row, our two-dimensional network. However, the problems we are focusing on are built with large unit cells, like 24 spins per every unit cells in Pegasus graph. So the tensor sizes needed to encode those problems are really huge. And we need to use more sophisticated methods, especially for approximating those boundary MPS. So making it work requires using a lot of technical concepts. So what makes it working? What are the key methodologies of our algorithm? This is more technical slide. So we use the sparse PEPS tensor structures to efficiently contract tensor networks with those extremely large tensor sizes. As I said, in the Pegasus graph, we have 24 spins per every unit cell. So the tensor sizes needed to encode these problems are up to 2 to the power 18. It's impossible to store them in the memory. It's impossible to perform calculations with such a huge objects. But they have their internal structure, which we call sparsity. And the structure allows us to work with not the whole objects, but we may use them as a building blocks and perform contractions with these building blocks, not with the full objects. And this is efficient strategy to handle those large tensor sizes. And we also use batched matrix multiplication, and we accelerate the computations on GPUs. We also use variational zipper algorithm for boundary MPS approximation, and in this zipper algorithm, instead of standard SVD for bond dimension truncation, we use randomized truncated SVD, which is faster. However, it may introduce some instabilities, which I will tell you about later. And we also tried the option for local dimensional reduction using loopy belief propagation. So let's imagine the Pegasus graph. We have 24 spins in every unit cell. So it's a large number of spins. But what if we select only the most probable spin configuration? Right? Because in Pegasus, we have 2 to the power 24 possible spin configurations in every unit cell. But we may select only the 2 to the power 20, for example, most probable spin configuration, and then use the branch and bound algorithm and work with those reduced space. And we also tested this. To find those most probable states, we employ those loopy belief propagation algorithm. And then I will show you the results with those local dimensional reduction of cluster degrees of freedom and full space tensor network results. You may see that sometimes it works, sometimes it's not. Okay, but maybe you are more interested in the results than the algorithm, so I will move to the metrics and the results. So to test the instances, we used two fundamental performance metrics, the energy metric and the diversity, the quality of sampling of approximate diverse solution of a spin glass problem. So in the first metric, in the energy metric, our goal was to achieve the lowest energy within some reasonable available resources. And we plotted as a relative energy difference above the best solution, where this E-best is the best solution that we got, but by putting together the solutions from all tested solvers. And in the second metric, we probe the quality of sampling of diverse approximate solutions of spin glass problems, and our goal here was to select from the set of available all solutions with energies that are within given approximation ratio, the largest set of independent solutions. What the independence in this context means, we call two solutions independent if their Hamming distance is greater than r times n, where n is the system size and r is the distance threshold. So in other words, let's say the diversity of solutions equal 10 means that in the set of states, all states with energies within given approximation ratio, we have found 10 such states that every state in this set is far from every other state in this set by more than r times n. Apart from the tensor network based algorithm, we tested all the instances on the wave quantum annealer, and we also used this simulated bifurcation machine as a second classical solver. What is those SBM algorithm? It is quantum-inspired heuristic technique based on a numerical simulations of a quantum classical counterpart of those quantum bifurcation machines. So, in other words, what we have to do, we have to solve Hamiltonian equations of motions, which are differential equations, and solutions are encoded in their steady states. And the solution at the final time is at least a local minimum of the Ising problem. What are the key advantages of those SBM algorithm? First of all, it supports general geometries, so it can manage dense spin-spin interactions with high precision. It also can be accelerated with the GPUs. Okay, so now let's move to the results part, and let's start with the ground state search. So we tested both Pegasus and Zephyr instances. Here I'm showing you the results of random instances with couplings that are uniformly distributed in -1, 1 and without local fields. We also tested instances with non-zero local fields and also corrupted bias ferromagnet instances, but their performance is similar, so I'm showing you the simplest case of random instances without local fields. And apart from the full space tensor network simulations, which is here marked by those green dots, we also tested those dimensional reduction of cluster degrees of freedom using loopy-Belief propagation, red and blue dots. And we selected from 2 to the power 24 possible spin configurations in every cluster, 2 to the power 20, or 2 to the power 16 possible spin configurations. And the vertical axis measures the solution quality, here as relative energy difference from the best solution. And the horizontal axis measures the time of each algorithm, where every point indicates the best solution at the end of the single algorithm execution with some set termination criterion. And we tested instances with different sizes, 216 spins up to 5,000 spins. And you may see that tensor networks without those dimensional reduction and tensor networks with dimensional reduction to 2 to the power 20 states in every cluster for the smallest instances, they are able to identify the ground state. However, tensor networks with dimensional reduction to 2 to the power 16 states in each cluster, it can't find the optimal solution, and this is due to the fact that the ground state is no longer supported on this reduced state of possible spin configurations. For the larger problem instances, like with 1,000 spins and 5,000 spins, tensor network method gives us the solutions with energies that are below approximation ratio 10 to the power -2. However, we are not able to identify the ground state. And D-Wave, quantum annealer, and SBM machine, they identify the solutions with very high precision, sometimes optimal solutions at very fast time scales. And as for the simulation time, you may see that SBM is fairly competitive with D-Wave. And tensor networks, they need orders of magnitude more time in their search than annealers and SBM. Zephyr geometry, however, proves to be more challenging for our tensor network method. You may see that we are able to identify states that with energies below approximation ratio 10 to the power minus 1, minus 2. And we expect this drop in performance may be related to the fact that in the Zephyr geometry, we have more these diagonal couplings than in the Pegasus graph. And this structure is more complicated, so the tensor network is more complicated, so it's harder for the tensor networks method to contract those structure, and it has its impact on the contraction stability. Apart from those random instances on Pegasus and Zephyr graph, we also tested tile planting instances, also on the Pegasus graph. Tile planting instances, they are instances that are constructed with a planted solution, so the ground state is known a priori. There are no i.i.d. Problems. So we took the instances from those papers, and they are defined on the square lattices with system sizes. We select those system sizes 10 by 10 spins, 20 by 20, and 40 by 40. And then we embedded them into a Pegasus graph. So after such an embedding, the number of spins has grown from 100 to 164, from 400 to 721, and so on. And to our surprise, for this class of instances, tensor network method works better than D-Wave and SBM. So for this smallest problems, both SBM, D-Wave, and tensor networks, full space tensor network method, they gave us the optimal solutions. However, for larger problem sizes, tensor network outperforms D-Wave and SBM. However, we are not able to reach the ground state, which is known a priori. But we are better, factor 3 better than SBM and D-Wave. So to our surprise, there are classes of instances for which the using of tensor network may be good. So there are some applications of our method. So let's move to the second metric. So we also check the quality of sampling in the framework of the diversity of solution. I said that diversity of solution equals 10 means that in the set of all states with energies below approximation ratio, here 0.01, we have found here in this case 8 such states that every state in this set is far from every other state in this set by more than r times n. So here we focus on only on the Pegasus instances, the largest Pegasus instances with more than 5,000 spins, and we set approximation ratio to 0.01, and we tested 2 distance thresholds. Large distance threshold r equal 1/2, and smaller distance threshold r equal 1/4. And you may see that for a large distance threshold, the total diversity is of the order of 8, and tensor networks are able to identify like 50–60% of those diverse states. However, for a smaller distance threshold, 1/4, the total diversity is of the order of 4,000, and tensor networks can give us only a small fraction of those diverse states in this case. D-Wave and SBM, they identify all diverse states for large distance threshold, and let's say complementary diverse states for smaller distance threshold, but together they identify all diverse states. And the fact that tensor networks for smaller distance threshold identifies only the small fraction of those diverse states, it may be related to the fact that the tensor network algorithm is deterministic algorithm. And it works with some width of search in the branch and bound method. And SBM and D-Wave, they are both probabilistic algorithms, so they are able to give us orders of magnitude more states in the results than the tensor networks. So here, for this R equal 1/4, we relax the criterion for diverse states. So this quantitative advantage translates to more diverse states found by D-Wave and SBM than tensor network. In the case of Zephyr, you may see that the behavior is very similar to Pegasus case. So we also tested the largest Zephyr instances with 2 distance thresholds. And for large distance threshold, total diversities of the order of 6. And tensor network method gives us like 50% of those diverse states and only a small fraction for large distance threshold. And D-Wave and SBM, they identify together all diverse states. Okay, but our goal was not only to solve optimization problems using tensor network method, but in a tensor network community, we wanted to better understand the limitations of the tensor networks in this context. So we wanted to understand why sometimes those contractions break. So we focused on smallest problem size, like the Pegasus instances with 216 spins. And we ran tests across different inverse temperature beta, different bond dimension, and numerical precision setting, like float 32 and float 64. And our main goal was to see how often the tensor network method can identify the ground state. This is shown here on the first plot on the panel A as the ground state success rate as the function of inverse temperature beta. And from this first plot, you may see that there is a trade-off between the resolution provided by a branch and bound procedure, which favors higher beta, so lower temperatures, and the stability of tensor network contractions, where smaller beta or higher temperatures allow for a more precise calculation of marginals. And this is a general observation that while working with the tensor networks, there is always a trade-off between the stability and the accuracy. So the first thing we had to do in our simulation, so we had to find the optimal temperature, the optimal beta. And from this first plot, you may also see that the higher bond dimension, the better the results, but this is expected in our simulations. And next panel, panel B, focuses on the truncation error. This is measured by the smallest retained singular value at the worst MPS cut. And from the both plots, you may see that numerical precision has no significant impact on the final results. This is very interesting for us because we thought that using 32 will somehow be better for us, but it doesn't significantly impact the results, at least with a reasonable beta range. However, things gets tricky with higher beta, so with lower temperatures where tensor contraction failures start happening. And then panel C shows the algorithm instability, because sometimes different runs produce different outcomes. And it shouldn't be the case because, as I said, our algorithm is deterministic. So every run of the algorithm should give us the same outcome. And sometimes it doesn't. So this may be linked to those randomized truncated SVD method which we use in the approximation of boundary MPS, which is good for us because it is fast and it works in a matrix-free way. So we can use it for those large objects. However, it introduces some instabilities which then our variational MPS algorithm cannot fully converge. This is the only point in our algorithm which is, let's say, more random. So the main problem with our method is those contraction instabilities in those cases. Okay, so now, as I have like 10 minutes, I would like to introduce those LHZ architecture. We heard quite a lot about LHZ yesterday, so let me briefly recap the basics. So whereas the wave focuses on specific qubit topologies, there are alternative quantum annealing architectures that address the limitations of those fixed hardware topologies. And one of the most promising alternative is the Lechner-Hauke-Zoller architecture, or LHZ architecture, which transforms a fully connected Ising model into a system of local constraints. So this is the original all-to-all Ising spin-glass model. On the left-hand side, here you have the logical spins ups and spin down. And then you can map it to a system of physical spins, where the physical spin is the pair of two logical spins that are connected through a coupler. For instance, this one, two, means that we have the spins 1 and 2, and the value is 0 because the spins are aligned antiparallel. Here, 1 and 3, the logical spins are aligned parallel, so the value is 1. And as you heard yesterday, there is this parity constraint relation. So in every closed loop, we have the even number of ones. And not only we have those physical spins in this representation, but also we have to introduce some constraints to the parity constraints, but also we have to make sure that indeed those physical system reproduces those logical system. And this is as this is the local interaction system with local interactions only, we can think of the tensor network representation of this system. There are many tensor network representation, but as LHZ can be expressed naturally as a tensor network, I'm presenting you two possible tensor network representation, the cross representation and the loop representation. In the cross representation, this is very straightforward representation of LHZ. We have two types of tensors, this, let's say, local tensors. They are corresponding to the physical spins. And we also have the parity tensors, which corresponds to those parity constraints in LHZ. This is very simple representation. However, one may think of another tensor network representations of LHZ. For example, loopy representation, where those blue parity constraint spins can be represented as 4 green tensors that are connected cyclically. And for a tensor network community, this representation is interesting because this is MPS, but with a periodic boundary conditions. So instead of this one blue tensor, we may use those 4 loopy tensors, green tensors. However, this representation is not two-dimensional. This is not Pep's tensor network. So to find the Pep's tensor network, the simplest way to do this is to contract every red tensor with its 4 neighbors, 4 green neighbors. Then we obtain those purple tensor with 8 legs. However, we may reshape it into rank 4 tensor, and then we obtain the Pep's tensor network representation. These two representations, they are equivalent. They are equivalent in the terms of energies they encode, and in the terms of constraints they impose. However, they differ in the underlying geometries. And in practice, this geometry may introduce some differences in the contraction stability, and we may obtain different outcomes, which you may see here. These are only preliminary results of the tensor network for LHZ, not published yet. But here we tested random instances from system sizes from 6 spins to 60 spins. And we tested it against SBM, simulated bifurcation. And you may see that for smallest problem sizes, both cross and loop representation, they give us the similar results. However, for larger system sizes, loop representation seem to be better than the cross representation. However, sometimes we are able to identify the ground state, but in many cases we are unfortunately not. Yeah, here we also have many problems with those contraction stability. We tested here, the results are for boundary MPS contraction method. However, we also tested coordinate transfer matrix CTM. However, it's not converging, surprisingly for us. But overall, these results, they confirm that tensor networks can be extended to fully connected problems, although numerical stability remains the main limitation. And that brings me to the end of my talk. So I'd like to conclude with saying that the contraction stability is the biggest issue of tensor network approach. But we also observe that the hardness of contraction grows with the lattice connectivity. Quantum annealers are really good solvers, but simulated bifurcation provides very competitive results and deserves more attention in these cases. And tensor network can be extended to fully connected problems like LHZ. I'd like to advertise before I finish. So our tensor network solver is available online. So if you are interested, you may download the code. You can use it yourself. You may solve optimization problems with tensor networks. So please take a look. More details about the solver you may read in this paper in Software X. Also, all of the data, all of the instances is available online, and more benchmarks, more examples is contained in this first paper. So before I finish, I'd like to take the opportunity to thank my collaborators for their contribution and hard work. And thank you for listening. If you have any question, I would be glad to answer them.
Any new questions? I might just be not being able to see, but I mean, I have a question. I don't know if this is possibly just more to do with my lack of familiarity with tensor networks than anything else, but I guess I didn't quite follow what the instability really means in this context, because if it's deterministic, again, I think this is more to do with my understanding of tensor networks. But yeah, where does that come from, and what does it really mean in the context?
Those instabilities, because if we use the standard SVD, then our contraction wouldn't be unstable.
Yeah, okay.
Unstable, right? However, we have to use those randomized truncated SVD because our tensors are huge. But we expect that maybe someday someone will improve those algorithms, and then the contraction will improve and we will get better results.
Mm-hmm. Okay, that makes sense. Okay, there's a question up there. Yeah. Oh.
Thank you for the presentation. I'm not sure I got it, but with tensor networks, did you say at the beginning that you were able to solve discrete problems? So that means that...
This Ising spin glass problems,
but still binary, so no pods or...
Binary, yeah.
Okay, yeah, thanks.
Anyone else? Okay, gonna come back down.
However, one may think of random Markov fields, and solving tensor network. It is also possible. But we are focusing on binary problems.
Okay, great. I mean, if there are no more questions, let's thank our speaker again. And